Okay, so these are examples for proton NMR spectra. First, this is the methanol molecules. As you can see, there are two types of hydrogen atoms, the red one and the blue one. For the blue one, this is CH, right? That is attached with very high En oxygen atom. So normally, hydrogen of sp3 carbon appeared at about 1 ppm, but because you have the effect of the En value, it takes electron out, electron clouds from the methyl group and make your methyl group lack of electron clouds. So now the external magnet can then fix the hydrogen atom tightly, and you need a higher energy in order to excite it from ground to the excited state. So this is why your hydrogen atom appeared at a very high frequency, 3 ppm. And for OH, this is even higher because of the hydrogen bonding, right? And hydrogen is now attached directly to the very high En oxygen atom, right? So it goes down to about 5 ppm. And next, this is the toluene. As you can see, it's composed of two types of hydrogen atom, methyl and the benzene ring. So as you can see, the benzene ring with the ring current, the movement of the electron around the benzene, so it's counteract with the external magnetic field. So by this circulation of electron creating a very strong internal magnet, and it synergistically emphasizes the magnetic moment that is interacting with 5 hydrogen atom in the red circle, and then your hydrogen atom feels with the stronger magnetic moment than usual, and it appeared at very far left at about 7 ppm. But the methyl group, because you have carbon right in between hydrogen and the benzene ring, so it drops down all the effects that we've already discussed. So hydrogen atom is dropped back to about 2 ppm. For carboxylic acid, as you can see, hydrogen of aldehyde attached directly to the carbonyl appeared at about 10 ppm. But now you have one carbon atom right in between carbonyl and H. So it's dropped the hydrogen back to 2 ppm approximately. And the hydrogen at carboxylic acid, which can be partially dissociated, right? Because this is acidic hydrogen atom, right? So it's dissociated, then your hydrogen has very low electron clouds, right? So it's very strong deshielded to the left hand. So this is offset 2 ppm. So that means this hydrogen atom appeared at 12 ppm, right? But this plot is stupid. It's plot at about 0 to 10, right? So actually it should plot it from 0 to 15, thing like that, so you can see this hydrogen in the picture. Okay, next, this is MTBE, methyl tetrabutyl ether. So as you can see, this methyl on the red color, this is sp3 carbon atom and nothing more. So it's appeared at about 1 ppm. But the methyl connecting with oxygen atom very high En, right? Because of the high En, oxygen atom takes electron out from the methyl group in green color. So this methyl group appeared at about 3 ppm, right? When it attached with oxygen atom. Now, come to this one. As you can see, we have 3 different types of hydrogen atom. First of all, we have red hydrogen, right, as I labeled over here, and then we have purple color hydrogen atom, and again we have green color hydrogen atom. For green color hydrogen atom, this is sp3 carbon attached with hydrogen atom and nothing more, so it appeared at about 1 ppm, right? So 1 point something here is the green color. Then we have carbon hydrogen attached with the carbon atom, which is next to the carbonyl group, so it should appear at about 2 ppm. So the red color appeared at 2 ppm, But for the purple color, because you have two carbonyl group, right? Normally one carbonyl group, your hydrogen atom appeared at 2 ppm. So sp3 carbon appeared 1. When you have one carbonyl group, it's plus 1 and appeared at 2. So if you have two carbonyl groups, you have to plus another 1, right? So it appeared at about 3 ppm. So the purple color hydrogen atom appeared here. So it's the combination of two carbonyl groups. So the effect is stronger than only one carbonyl group. And next, again, this is very similar to the toluene, right? For toluene, you have 7 and 2, right? This is silene. So again, your green color is belong to the benzene ring, and the blue color belongs to the methyl. So you have one carbon atom right in between benzene ring and your hydrogen atom. So your hydrogen atom is drops down back to the 2 ppm region. Right? Not only the position that you can gather the information from the NMR data, but also the number of hydrogen atoms as well. This picture, as you can see, the blue color, this is the integration. The integration here is the integration of the peak area. So at the very far left, there's nothing, right? And when you come to the peak area is increasing. So it symbolizes the peak area by this integration line in blue color. So here in the structure, you have the methyl group CH3 in red color, which is here on the left hand, and the green color on the right hand. This is because the green color is sp3 carbon normal, appeared at 1 ppm, but the red color is the methyl group attached with the oxygen atom very high En, right? So if you look at the ratio of green and red and green is 3 to 9 or 3 to 9 ratio, right? 3 to 9 ratio. So it's actually 1 to 3. 1 to 3. I would use this one. 1 to 3. This is the integration. Okay. So the integration here can give you some hint about the number of hydrogen atom in the molecules, the ratio. So you can have the ratio from the integration, and you can have a kind of environment from the ppm, right? So NMR normally give you this to very valuable data that you can use it in order to interpret the structure afterward. Now, for this one, I give you the molecular formula C6H12O2. Every time when you see the molecular formula, first of all, what you have to do is find the DBE, double bond equivalent, which is now equal to 6 minus 12 divided by 2 and plus 1, right? Carbon minus hydrogen divided by 2 plus nitrogen divided by 2, but you don't have nitrogen here, and then plus 1. So as a result, you have 1. So double bond equivalent equal to 1. That means you may have two possibilities. First of all, you have one double bond in the structure, and secondly, you have one ring in the structure. Okay, so you have nothing else than this. So what you have to do is count the type of hydrogen atom. As you can see, we have 4 different signals, right? So that means 12 atom of hydrogen in the molecules, composed of 4 types of environment, right? With the ratio of 0.5, 1, 1.5, and 3, right? So in total of 12, right, it have to be 1 to 2 to 3 and to 6, right? 1 plus 2 plus 3 and plus 6 is equal to 12. So you have 12 atom of hydrogen atom. And if you have number 3, so that means it should be CH3, right? This one should be CH3. I will use yellow color instead. And for 6, right? So you don't have CH6. That means for this 6, you should have 2 of the CH3, 2 of the methyl, right? It's quite something, it should be something like this. And then again, you have 2, so it should be CH2 maybe. Okay. And what else? So we are now using 2 carbon on the red color, 1 carbon in yellow color, 1 carbon in green color. So you have 4 carbon already, right? So this one should be maybe carbon or maybe OH, right? Because you have only one hydrogen atom. It may be OH or it may be carbon with 1 hydrogen atom. I'm not sure. But anyway, as you look at the number 2 point something, the position 2 point something, 2 point something meaning that you have carbonyl group, right? Or aromatic group, right? So now I want to guess that we have the carbonyl. So if we have carbonyl group, carbonyl have 2 side, right? So one of the side should be CH3, right? And one of the side, the other side here, should be CH2. Okay. Now you can start connecting things together, right? So now we have black carbon, green carbon, yellow carbon, 3 of them, right? And you also have red color carbon atom as well. The red color carbon atom is only 1. What else should we have? And you have purple color here. But anyway, 2 of the red carbon, 2 of the methyl group, CH3 and CH3, they are appeared at the same place, right? So you have to attach with the same atom. Now you have 1, 2, 3, 4, 5 atom already. You have 1 atom of carbon and 1 atom of oxygen left. But oxygen you cannot put it here because it will end this molecule, right? So you have to put it with carbon atom maybe. So it should be carbon atom. But your carbon atom has 4 bonds. But this is just 2. You have 2 bonds left. If this is, oh my, wait, I have to use different color. I will use this shit color, sorry, brown color for carbon. So one of the bonds should be like this, and the other bond shall connect to oxygen atom because you have nothing else. So that means at the end, this H in purple color belongs to OH. Right? So it's like Lego thing like that, puzzle. You have to connect things from hints that is given in the spectrum by the position and by the integration over here. Okay, no? I am okay. So I guess you have to be okay. Okay, thing like that. So this is another question, right? We have 6 molecules and we have A, B, C. Okay, A, B, C. So you have to use 6 molecules and this graph A, B, C to like pair up which molecules belong to which graph. So first of all, in this graph A, you can see that we have 3 different types of hydrogen atom, right? But for the first molecules, you have just 2 different types of hydrogen atom. No? So you have purple color of benzene ring containing 4 hydrogen atom, right? And you have pink color CH3. So it's not A for sure, because for A you have 3 different type of hydrogen atom. Now for second molecules, you have purple color of benzene ring containing 4 electron, 4 hydrogen atom, and you have the methoxy group, right, in pink color. So you have only 2 types. Okay. Third molecules, aromatic again, and this pink color hydrogen atom of alkyne. So you have 2 types of hydrogen atom. Now, this one, you have 2 of the methyl, which is exactly the same, right? Environment, same environment. And then you have pink color of the alkyne, and then you have green color of the OH. Okay? So you have 3 types of hydrogen atom. So it's quite likely to be A. But anyway, you shall ask for other molecules as well. Then this one, you have purple color, which is different from this CH, and also different from this CH2, and then again different from this CH3. So you have 4 different types of hydrogen atom. Right? And the last molecule, firstly you have CH2, which is the same, right? And again you have CH3. This 2 of CH3 is the same as well, so you have 2 types. The only one molecules that have different 3 different type of hydrogen atom is this one. Right. So this is the A. Right. Okay, I will put A over here. You have CH3, and then you have like OH in green color, and then you have alkyne. I would label it in pink color, and this is H of the alkyne. So the purple color CH3 is sp3, right? So 2 of the CH3 appeared at 1. Then you have OH, and then you also have the alkyne. So they are very similar, appearing at about 2 ppm. Okay, we may not very sure that which one belong to alkyne, which one is belong to OH. Okay, because it's very close together, right? Very hard to distinguish between them. But okay, we find at our best we know it should be something like this. Next, 2 types, and it at 7. So at 7, meaning that you have benzene ring. Okay, because it's 7. Then 3 something. So for benzene ring, you have first 3 molecules containing benzene ring. But the first one here, CH3, should appear at about 2 ppm, if you can remember, right? So this approximately 2 ppm. And for alkyne, it's normally about 2.5 ppm, right? And the benzene ring connecting with oxygen atom, very high En, it should be about 3 to 5 ppm. So this should be the second molecules. So OCH3. Okay, para position is like this. Okay. So the integration seems to be okay as well. So as you can see, the integration over here seems to be 4 to 6 ratio. Okay. It's like the first spectra seems to be 1 to 1 to many, right? So it's actually 6. So you can double check the position and the integration. Last, this one. So you have 3 something and 2. So you have just 2 type without without the benzene ring. So it have to be the last molecule over here, right? So it is 1,2-dibromo 2-methyl propane, right? 1,2-dibromo 2-methyl propane. So So it's this one, right? And as you can see, we have CH2 over here, and we also have two of the methyl group over here. So the methyl group is far from Br. So two of the methyl group with integration of 6 appeared at about 1 something, very far. But the purple color, because it's very close to the bromine, it's very close to the bromine, is 3 something. So the purple color is the CH2, and the integration is okay. It seems to be 2 to 6, right? So this is how we can use the integration and the position to identify the organic molecules. Next time we'll talk about the splitting pattern, which is very useful for the structure elucidation. So see you again next time. Thank you for today.